Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the basics of carbohydrates, and in that we are discussing the analysis of 1,2-diols. As we know that carbohydrates are polyhydroxyaldehyde or the ketones are optically active or on the compound on hydrolysis gives that unit is known as a carbohydrates. So first in the long where there is no such modern technique available for determination of the unknown structure of the organic compound, that time, very old time, very long time back, the chemists are usually trying to find out the structure of the unknown compound of the organic compound, and they are using various techniques. And because nowadays we have modern technologies such as UV, NMR, mass, IR, X-ray diffraction, Chem. These are the various techniques available today. Heat core, depth, cozy, heat cozy. This type of the various technique are available today. We can find out the correct structure of the organic compound, but a long back there were such type of the technique were not available. So that time this technique for specifically in carbohydrates and the alpha amino acids, these techniques are used that time chemist. So what is that? Yesterday we have seen if how adjacent hydroxyl groups are present, how the carbon-carbon bond get cleaved, that we have seen yesterday. Let us see again oxidation by HiO4 periodic acid. As we know that HiO4 is known as a periodic acid and is used as an oxidizing agent, and which cleaves carbon-carbon single bond if both the carbon have a hydroxyl group, or if OH and NH2 groups are on adjacent carbon atom, the carbon atom whose bonds are cleaved are converted into CHO group, and if this can 3 OH group on adjacent carbon atom, the central carbon is removed as a formic acid. Yesterday we have seen how the formic acid is generated, how acetaldehyde is generated, how carbon dioxide get evolved. Depending upon the structure of the starting material, they are confirming that what kind of the starting material or what type of the structure that organic compound have, or what type of the carbon skeleton that unknown compound has. So they are determining. So let us see here one of the example over here. There we have seen some of the question regarding that. So let us move on to the next one. Suppose as let us see one more question over here, so that we trying to solve that. Treatment of plus glucose. Treatment of plus glucose with HiO4 gives result that gives a result that conform the aldohexose. Conform the aldohexose structure. What product should be formed? What product should be formed? What product should be formed, and how much HiO4 and how much HiO4 should be consumed. That's the question. Again, see the question here. What is that? Treatment of plus glucose with HiO4 gives result that conform the aldohexose structure. What product should be formed and how much HiO4 should be consumed? That's the question. Suppose, and we know that the aldohexose structure, aldose and hexose means 6 carbon atom. As we know that the structure of glucose CHO, if you write over here the structure, let me draw the structure properly over here. And as we know that we are familiar with this structure, glucose 1, 2, 3 and 4 lines are there, and then here you can write as a CH2OH, right? And 2OH on the right hand side, 1H here, OH here, and rest of the thing you can place the hydrogen atom. This is the structure of glucose as we know that, right? Now how many carbon atoms are present here? 1, 2, 3, 4, 5 and 6. We are trying to answer this question. So this is the structure of glucose as we know that, right? And now when it is treated with HiO4, right? What product should be formed and how much HiO4 should be consumed? So what product should be formed? The product are, if you observe this structure carefully, look at that C double bond O carbonyl group. Here is a hydroxy and 1 mole can be consumed over there. And now another one, there is a hydroxy group, another one and another one. Here also as they are adjacent one. Look at 1, 2, 3, 4 and 5 molecules. 5 moles of this HiO4 get consumed over here. 5 moles of HiO4 get consumed here, right? So here, and what type of the 5 moles of HiO4 get consumed here? Let us see here, right? And what type of the product? Look at here, aldehyde. So that we are going to get what type of the product? It will produce the formic acid, right? Formic acid here, one formic acid here, another one, second, third, fourth, fifth, and here you will get as a formaldehyde. And therefore, how many formic acid you are going to get? 1, 2, 3, 4 and 5. 5 are the formic acid, C double bond OH, and this one, last one is a primary alcohol like this, CH2OH. Here you will get as a formaldehyde, C double bond O and this H. This is called as a formic acid, and this is a formaldehyde. So in this way, you have to write 5 moles of HiO4 get consumed here, or you can write as a separately the product form. So what product should be formed? These are the product: formic acid, 5 moles of formic acid and 1 mole of the formaldehyde. These are the product formed. And how much HiO4 should be consumed? So let us, the answer is here, 5 moles of HiO4 should get consumed over there. So in this way you have to answer this question. Now let's move on to the next question. What the next question says, let's see over here. What will be the next question, or what is the next question says? Let's see here the question number. Next one, what it says: identify each of the, what is that? Identify each of the following glucose. Identify each of the following glucose. Each of the following glucose derivatives. Each of the following glucose derivatives. That's the question over here. Identify each of the following glucose derivatives. How we can identify these derivatives? They have given here A plus, what is that? A plus 4 HiO4, 4 moles of periodic acid, and they produce 3HCOOH, formic acid, 1 mole of HCHO, that is a formaldehyde, and next one is a plus will be this one, CHO aldehyde group, and COOH, one is a acid group. So this is a compound they have given there. So from that we are going to find out what will be the A over here. So let us see one by one, because there are the 4 they have given, and you are going to find out A, B, C and D structures. So what will be the structure of this A? If you observe this reaction carefully, what do you see over here? Look at here. A plus 4 HiO4 gives 3 moles of formic acid, 1 mole of formaldehyde, and 1 mole of this type of the compound. So do you think what would be the structure of this A? That we are going to find out. And suppose we have a structure. Let me A structure. Suppose A structure has this one, COOH. Then there will be suppose as this type of the compound over there. Suppose 1, 2, 3 and 4. Let me draw one formaldehyde is there. So ending must be as a CH2OH. 4 moles are consumed. So there OH, H, then OH, H. Now then what we can call it is here is here HO, H, and now OH. And this is a structure of, if you know, this is a structure of gluconic acid, right? Gluconic acid. This is a structure of gluconic acid, as we know that. And when glucose is treated with Br2 in presence of water, that is a mild oxidizing reagent, what it will do? It will oxidize the aldehyde group into as a carboxylic group. And now look at, there are 4 molecules. One aldehyde is there, formaldehyde. So 1 mole get consumed over here. Look at, there are 3 formic acid. So here they are adjacent. So 1 formic acid, 2nd formic acid, and there is a 3rd formic acid, and here this side you will get that one. Only 4 are there. 1, 2, 3 and 4, and if you treat with this 4HiO4, it gives this type of the compound. Means the A structure has got as a gluconic acid. So in this way you have to find out you have to identify each of the following glucose derivative. So this is one of the derivatives we have seen over here, right? So now let me give one more here, second example over here. Now we got first one, now second one is a B. So here B plus how many HiO4, let me here 5HiO4, it produce, what it produce? It produce 4H formic acid, COOH, and plus one is a, what we can call it as a 2R formaldehyde group, 2HCHO group, right? So this is the compound, is a gluconic acid we got, and now is a B is a glue. So here 5, right? And now what will be the, how do you think that B? Well, because all are the, here identify each of the following glucose derivative that we are finding. Here 5 moles of periodic acid get consumed. Think over there, and we got the 4 molecules of what we can call it as a formic acid, and 2 moles of the formaldehyde. So that if you think a moment, what do you get? Do you got the idea what could be the structure of B? Let us see here this structure B, the structure of B. If you look at it, there are formaldehyde, means in a glucose derivative, suppose if you remember here CH2OH, and this side also CH2OH, and as we know 1, 2, 3 and 4, OH, OH, H, H, HO, H, OH and H. If this is a structure, means glucose reduced with H2 in presence of nickel, the glucose get reduced in this way. And now if you look at, there are the 5 moles, means here if you see 1 mole, here another HiO3, and third one, this is a 4th one, and 5th one. Look at, there are 2 terminals are there. 2 terminals CH2OH, primary alcohol gives you the aldehyde, whereas this middle one, 1, 2, 3 and 4, they will produce this 4 formic acid. Got it? It is so simple, just you have to remember how the derivatives of, because we are finding or we are identify each of the following glucose derivative. In a first case we have seen there is a gluconic acid. A is having as a gluconic, A is a gluconic acid, and B we got, that is a sorbitol, right? Sorbitol. This is another derivative of that. And now let's see third one. Structure number C we are going to find out over here. C plus is given 3HiO4 produce the compound 2 moles of formic acid HCOOH, and plus how many moles of other, there is a CHO and COOH, that is the compound they have given. Now there, what could be the structure of this compound? So let's see over here 3 moles are get consumed, right? So here the C, what could be the structure of this? Look at here, 2 formic acids are there, and this is a one such type of the group, and so 3 moles are get consumed. And what could be the glucose derivative we are trying to find out? Let's think over. And then suppose you have a structure of C like this. Suppose here this COOH means, let us see here COOH, and then if you see that is C again COOH, suppose over there, that is a not glucose. C, suppose we know that as a gluconic, only one, this we have idea, there must be as a gluconic acid, and therefore this 1, 2, 3, 4, and finally CH2OH. This is a glucose structure of gluconic acid, as we know that H, here HO, H, and here OH, and hydrogen atom on this side. So this is the structure of gluconic acid, right? Gluconic acid once again. And if you there are 3 moles are there. 3 moles means what? 1 is here, so that we will get this one, right? Then 1 mole, then 2nd mole, then 3rd mole, and rest of the thing we are not going to because only 3 moles are there, so that from this, so how many 1 is there, 1 will give this one, and 1 and 2, this 1, 2 are getting as a this compound, rest is not given, so therefore don't think about the other thing. So this will be the structure of this derivative, glucose derivative. So this is there. Now let us look at as a last one. What is that? D plus, there is a 4 moles of HiO4, 4 HiO4. It gives, what it gives? 4 moles of formic acid, COOH, and plus the product is the same, CHO, then COOH. Then what could be the structure of D? What do you think? Again is a gluconic acid. Structure of that it's again as a gluconic acid. 4 moles are there, and this one CHO, that means again is a structure is a gluconic acid. And as we know that D having as a structure like this, COOH, 1, 2, 3, and 4, and then right as a CH2OH. As we know that OH on the right hand side, and then 1 OH on the left hand side, hydrogen OH and OH. Here 4 formic acid, if you break from here and not from there, this one we are getting as a this compound, right? 1, 2, 3, and 4 are there. So 1, 2, 3, and 4 we will get over there, and 1 formaldehyde is not written over there. So only 4 moles are get consumed, you will get as a this type of the compound. Formaldehyde is not given. So this is a gluconic acid structure once again. So in this way we can analyze the 1,2-diol present in the organic present in the carbohydrates. Now let us move on to the next point. What will be the next point we are going to discuss over here? Let's see, because we are discussing about the basics of the carbohydrates. So here basics of carbohydrate, let us see here. Optical isomerism in glucose. Optical optical isomerism in glucose. That's the point of discussion over here. And as we know that the structural formula of glucose shown that it contains 4 chiral. We know that the structural formula of glucose, it containing as a 4 chiral carbon atom, and you have learned that every chiral carbon can have 2 distinct special arrangement of group around it. In other words, 2 distinct configurations are possible for each of 4 chiral carbon of glucose. Stereo structure of glucose is therefore one out of the several possible stereo structures of an aldohexose. Do you know a structural formula containing n number of chiral carbon can have maximum 2 raised to n number of stereo structures or optical isomers? An aldohexose therefore can exist as 16. 16 means what? There are 4 chiral centers. We know that the structure of the glucose is this one, CHO. Then generally we are writing here CH2OH, and middle 1, 2, 3 and 4. So as we know that OH on the right hand side, then one OH here, H, OH and the hydrogen, and this is the structure of D-glucose. And chiral center means what? The carbon atom carrying 4 different group is known as chiral center. If you observe this structure carefully, look at this carbon atom, we can show by the asterisk over here another chiral center, one more chiral center, and so if you count the chiral center in a D-glucose or in a glucose, there are 4 chiral center, and if you write as a 2 raised to 4 is equal to 2 into 2 into 2 into 2, 1, 2, 3, 4 times, so you will get the 16 isomers, and therefore out of that 16 isomer, one of them is a glucose. So this is the structure of glucose, and this glucose, as we know that we can get from the arabinose, right? So this is there. Can you recall what are the ways to represent 3-dimensional structure of an organic molecule? Because there are the 4 conventional ways to represent the organic molecule on the blackboard, or to study its 3-dimensional structure. How is a Fischer projection formula drawn? Do you know that? So can you recall how is a Fischer projection formula drawn? There are first one Weiss formula, or what we can call as a flying formula. Second one is a Sawhorst or Andrun formula. Number 3 is a Newman projection formula, and number 4th is a Fischer projection formula. And Fischer projection formula is a very useful as far as a carbohydrate chemistry is concerned, because all the carbohydrate molecules are generally represented by using as a Fischer projection formula. And as we know that there are the certain rules, according to this formula, the molecules are written vertically. The carbon framework is always kept vertically, and so according to and at the top there is a most oxidizable groups are at the top, and in that way the other atoms are arranged in other atoms are special arrangement in that special arrangement of a group around that carbon atom. So it is beautifully arranged over there. So now on the basis of very elaborative chemical evidence and measurement of optical activity of various chemicals involved Emil Fischer, a German Nobel laureate in 1902, German laureate, 1902, determined the configuration of the 4 chiral carbon, that is this one. If you number this 1, 2, 3, 4, 5 and 6, so chiral center at C2, C3, C4 and C5 he determined in a glucose, and use write a structural formula of glucose, shown all the bond in the molecule, number all the carbon in the molecule, giving number 1 to the CHO carbon atom. So that is make the chiral carbon in the molecule with asterisk, as I already shown over here. How many chiral carbon are present in a glucose? There are 4 chiral carbons are present in the glucose. So then there is a gluconic acid, and so that are the some of the structures are drawn over here. So figure shows the Fischer projection formula of glucose and gluconic acid and saccharinic acid. So saccharinic acid must be as a COOH over here. So let's see how the structure of that 3 structure gluconic acid, or what we can call it as a saccharinic acid. This we can call it as, this is a structure number first. Let us consider over here, and one more derivative of that, if it is treated with so OH, we are getting 1, 2, 3 and 4. Here you can write CH2OH. This you can call it as a structure number second, OH, OH, H, H, then HO, H, here OH and hydrogen. So there are also as a 4 chiral center, and this is a structure of gluconic acid. This is a glucose, this is a gluconic acid, and because from glucose we can obtain we can derive the gluconic acid. Just this glucose treated with Br2 in presence of water gives this one, or we can get here COOH, then 1, 2, 3 and 4. Let us see here CH2, here is a COOH, right? COOH. Once again here OH, H, H, OH, OH, H, here OH and hydrogen, and this is the structure number 3rd. This structure number 3 indicate as a gluconic acid. How do you get this one? From this we can prepare just by treating this Br2 in presence of water, right? Water you will get as this one, and if this treated with again concentrate HNO3 dilute HNO3, that primary alcohol get converted into as acid. So this is a strong oxidizing reagent, this is a weak. So from this also, if you treat directly this dilute HNO3 you will get as this type of the gluconic acid. This is a saccharinic acid, as we know that this is a saccharinic acid. This one is known as a gluconic acid, and this we know that this is a structure of D plus glucose, right? So these are the different structure. These are, we can call it as a derivatives of that glucose, and these are the, and now this figure shows the Fischer projection formula of glucose first, gluconic acid second, and this is a saccharinic acid third. And glucose is an optically active compound and has its specific rotation. This glucose has a specific rotation, is as we know that here is a 20D, it has plus 52.7 degrees. So that is a specific rotation. It can rotate the plane of polarization right hand side, and its optical activity is found to be, optical rotation is found to be 52.7 degrees centigrade. So that is a very important as far as some competitive exam point of view is concerned. So you remember this one. And due to its dextro rotation, glucose is also called as a dextrose, and the designation of plus glucose or D-glucose implies the dextrorotatory nature of the glucose, and D-glucose is another designation of glucose which is more common, and these designation indicate the configuration of glucose rather than the sign of its optical rotation. And so I think we have learned these are the sum of the point regarding that glucose. Then next one is a DL configuration system. And DL configuration, why that DL configuration system is used, as we know that this is a relative. So let us talk about this DL configuration. When just now we have seen as a optical isomerism in the glucose, because we are talking about just as a basic thing which are involved in the glucose molecule. Now let us see here DL configurations, right? DL configuration system, D or L configuration system, configuration, DL configuration system, configuration system, DL configuration system. And here we can see here the prefix D or L in the naming of the compound indicate relative configuration. These are known as the relative configuration of a stereoisomer, and it refers to a particular enantiomer of glyceraldehyde, and glyceraldehyde has one chiral carbon which is at C2 and exists as a 2 enantiomer, and these are represented by the Fischer projection formula. See this figure, and as we know that the structure of glyceraldehyde CHO, then we are writing here OH on the right hand side, and here CH2 and OH. This is known as a D-glycerol. Why it is called as a D-glyceraldehyde? There is a one chiral centers are there. According to as a bonds up, we know that 2 raised to n means 2 raised to 1 is equal to 2 isomers are possible. One is a D-glyceraldehyde, D plus glyceraldehyde, you can call it a D-glyceraldehyde. And now if you put as a mirror over here, is a mirror. What do you see? This OH on the left hand side, HO, and that hydrogen atom goes on the right hand side, and rest of the top CHO group as well as bottom CH2 OH group that remains as it is. This is known as a L, because that hydroxy group, if you see this carefully, if you observe this structure carefully, at a C2 carbon atom, hydroxy group are on the left hand side, and therefore it is known as a L glyceraldehyde. L minus, you can call it, or L minus glyceraldehyde. Glyceraldehyde. So in this way we can designate and we got that the enantiomer, and as we know that enantiomer means what? They are non-superimposable mirror images is known as a enantiomers. Look at our two hands, they are enantiomers of each other, means they are non-superimposable mirror images are known as a enantiomers. And here this D-glyceraldehyde and the L-glyceraldehyde, they are the non-superimposable of each other. Conventionally, plus glyceraldehyde is represented by the Fischer projection formula, having OH group attached to C2 on right hand side, and this configuration is denoted by symbol D. And similarly, configuration of minus glyceraldehyde is denoted by symbol L. All the compound which can be correlated by a series of chemical reaction to plus glyceraldehyde are said to have D configuration, and the compound which are chemically correlated to minus glyceraldehyde are said to have L configuration. And this is the system relative configuration of chiral compounds and what is that absolute configuration or somewhat detail we will see, I think, in the next lecture. Let us stop today here. Have a nice day. Thank you.